know.
Yeah.
Okay. Yeah. Don't post this on YouTube, but for you guys to watch.
Don't worry.
It's okay. So first of all, congratulations on being here. We're so proud of all the extremely hard work that you've done to build a car. You know, while going to school during a pandemic, it's so incredibly difficult, and most of us, if not all of us, are former competitors, so we understand how hard you've worked, how little you've slept, and so we hope that these notes will help this team, help next year's team, help all the teams after, just continue doing better and better and better. So yeah, your team should be very, very proud. And then what we're looking for in the design event, okay, so it's one thing to build a car, but we're looking for all of the math behind the car. Okay? So we're looking for justifications, for examples. This part is strong enough to carry the load that we calculated it would, you know, this was the load that it would encounter while the car is driving. This part is strong enough to survive fatigue because it has many loads that it has to survive. Or if a part, you know, a lot of times stiffness is more important than strength, so it's plenty strong, but then you have to do even more to it to make it stiff enough, and the calculations behind that. And so kind of every single part of the car, we want to see all of the math that you've done, and we want to see that you're doing math as opposed to just, you know, buying a kit and putting it together is not the same as the person who can create the kit for someone else to put together. So that's the engineering that we're trying to get to make sure that you have the skills to create something that someone else can do, and that the math, you know that it will be strong enough or stiff enough or that the car will be fast enough before you've made any parts, before you've put any parts together. It's the prediction that you're trying to do with the math. Does that make sense? Okay. Okay, so just be ready to show calculations for, you know, all sorts of different loads across the car, especially on the frame side. And then where it's harder to put math to it is more having good load paths. So, you know, the load has to go from the tire into the frame, and we do that with a nice straight line with the push rod into the rocker, as opposed to if the push rod was bent, that would be bad, and that's just true everywhere. You want the load path to change direction as little as possible, and then when it's a component that changes the direction of the load path, like the rocker, then that's probably a place where you want to do a bunch of calculations to make sure it's strong enough, because the loads are going in all sorts of different directions, and it's a really serious part of the car. And then this is, you know, this is simple calculations, and it's a little more complicated calculations for that. Specific to the frame, what design judges are usually looking to talk about, and this is also specific to any sort of automotive design, is the torsional rigidity. So the twisting stiffness of the frame, and making sure that it is stiff enough that when you tune the suspension, springs, shocks, anti-roll bars, you can read about the relationship between how stiff the frame needs to be, so that when the car rolls, it doesn't just twist the frame. When the car rolls the front and the rear, if you have a very stiff rear suspension and a very soft front suspension, right, and the car rolls, you don't want the front suspension to roll and the frame to twist and the rear suspension to not move. You want the frame to move and be stiff in between. So there's a relationship in between the suspension and the frame, and that's usually what we're expecting to talk about on the frame side. You can do a real simple beam FEA. I think you mentioned you had SolidWorks, and sometimes there's an FEA package in there. So you can just do the real simple beam FEA for a tube frame, and you can try out different frame designs, because you're just drawing the sketch from point to point, and say, what if we put the triangle here? What if we put the triangle here? What if we make this tube bigger or this tube thicker? You run that real quick. You write down how stiff it was. You also write down, you know, set up a sheet to calculate an estimate of how much the tubes weigh, and then you can try all these different designs and arrive at one that looks like it has a very good stiffness to mass ratio. So you can just do those experiments. You can run a bunch of FEA, you know, keep it simple so it doesn't take very long. Just very simple one-dimensional beams. You fix it. What I generally like to do, because we care about the suspension, so I will fix I'll fix this point and this point, fix wherever the rear shocks go into the frame, fix those 2 points, and then apply a twisting load to wherever the front shocks are, the front rocker points. And so that way it'll twist the frame just like the suspension tries to twist the frame. Okay? And so that's, you know, on a fairly modern computer, you know, those will take a few minutes to run each simulation. So you can sit down just in a day and you can try a whole bunch of frame designs and say, look, this one's really light and really stiff. This one's really heavy and really soft. Let's go with this one. Let's see. On the aero side of things, it starts with cooling. So work with your powertrain team to figure out how much power needs to go out of the cooling system to keep the car cool, and then achieving enough mass flow. So what I would like to see is a plot of the cooling capability of the car versus speed. It's not going to cool, when it's going slow, there's not much flow, it's not going to cool as well. So you've got the fan, and so then you can add that on the plot. Say the fan helps us keep it cool at speed when it's slow, and then at speed the airflow is keeping it cool. Just in general, you know, kind of getting to a more holistic vehicle dynamics, which is, especially if you start thinking about putting wings on a future car, you need to tie it all the way back to the acceleration of the car, the cornering of the car, and the braking of the car. So calculate for the car, and you can start really, really simple. You know, how hard can the car accelerate from 0 to top speed? You know, and then you can calculate really simple how. You know, what is the cornering G that the car can do around a skid pad, and then how hard can the car brake? And you can start with a really simple calculation, gradually make it more complicated. So do the calculation, and then go out in the parking lot or wherever you test this car and test the acceleration and compare it to the simulation. And so then you use the car to make the simulation better, and you use the simulation to make the car better. And then just, you know, you'll have all those numbers from getting better, and bring all those numbers and have those ready to show us in the design briefing. You know, the tablet was nice. You know, if you want to do that, to have a way to, if you want to have a binder full of all of the papers put together, that's fine. Just as long as you have showing all of the math for all of the work that you did throughout the year. That's what we're looking for. If you, and we had a talk yesterday, but if you seriously analyze the data, you can drive a video game. But if you download the data and you process all of the data and you're studying all of these things, it's if you take it seriously, it is a serious tool. You know, it just like the simulations and your calculations for acceleration and skid pad and braking, they're not going to be perfect, but they'll help you develop engineering insights to make the car better. You'll still see, what if we did this? You change the number in the calculation, you change the number in the simulation, you see what effect it has. You do the same thing in the setup of the video game. You change the number, you modify the car, you record the data to see what it does, and you can learn an immense amount from that. And then apply the same data gathering process, whether it's a stopwatch, whether it is what my team used to do. We'd put a zip tie around the damper, and that tells you the maximum amount of travel that you get. So it doesn't give you the graph of everything, but if you want to go in the parking lot and run a simple test as far as how much does the car, how much does the front squat under braking, you can do that. You just put a zip tie on, you say, oh, it moved this much. How much does it squat on a launch under acceleration? It squats this much. How much does it roll? Just do a real simple test and then stop, and then you measure it. So you find real easy ways to try to figure out how to measure these things in addition to the stopwatch. You keep the track really simple, and then you take those little pieces of the track and you stitch them together into a simulation of a big track, as opposed to just trying to start off simulating the entire autocross. You can see if it makes it faster or slower, but you'll have better opportunities if you see that we're going the same speed in the slow speed corners, but now we're going faster in the high speed corners, so you know where the advantage comes from. We're losing acceleration, but we're gaining cornering, or whatever the trade-off is. Does that make sense? Yeah. Yes. All right. Any questions before I hand it off to somebody else?
¿Alguna pregunta?
No entendí mucho, pero...
¿Alguna pregunta?
Solamente entendí lo del programa, que hay que simularlo hasta en un juego, ¿no?
No, hay que simular todo. Hay que simular todo, pero aparte hay que probarlo todo. Y esa es la razón por la que quiero que lo prueben antes. No lo terminen un día antes.
¿Qué clase de mexicanos seríamos?
We work for you for the next hour.
Antes y no un día antes.